And Eric, which one's lower energy?
The triplet.
This one. Why?
Because opposite lower energy than nose.
No. It's the Hund's rule. All right? To form the triplet, what must be the symmetry of the spins?
The spins have to be the same.
Aligned. The spins have to be symmetric.
Symmetric.
And then that
Therefore, what is the spatial symmetry?
therefore the space is anti-symmetric.
The space is antisymmetric. If the space is antisymmetric, what does that tell you about the expectation value between the separation?
They're closer together.
That they're
Divergence.
further apart.
Right.
The antisymmetric spin, the antisymmetrics. So again, guys,
Antisymmetric space means they're further apart.
you're going to have to get this right, and it's going to make your heads hurt for quite a while. Let's do it. Everybody heads up. Space. So spin, symmetric or antisymmetric?
Symmetric.
Symmetric. Therefore, what type of space?
Anti-symmetric.
Antisymmetric space. Let's get your inter-electron separation.
Minus, so it's
Further apart.
yeah, so it's minus-
Further apart.
Yeah.
The further apart means I have less of a electron repulsive energy, and therefore it's at a lower energy. This one, perfectly fine. All right? This is going to have an antisymmetric spin. Therefore, it's got to have a
Symmetric space.
symmetric space. The symmetric space lets two electrons get closer. That increases the total energy of the system. And so this one has a higher energy, this one has a lower energy. All right, so if we look at figure 5.2 for helium, they spell this out completely. So we'll look at the triplet P and the singlet P. So this is the singlet P, and then this is the triplet P. And if you look over here for energy, so this is 0, this is big negative number, so energy in EV. And if you look over here for the singlet P comes down to about like 3.5 EV. All right, and the triplet P comes down to about minus 4 EV. So, if you take helium and give it a little bit of external energy, right? So you excite one of the electrons up and you excite it into the n equals 2, L equals 1 shell. What is going to be the most likely configuration after everything is kind of like settled down?
The 3P.
The triplet P, where the spins are aligned. All right? And that if you wanted, you could excite transitions between here and here. If you had, I mean, that's hard to do because actually you can't do it. You have to change orbital angle moment. But there are other ways to excite from here to here. You can go. All right, and so for helium, these two configurations are given names. The singlet states are called parahelium. All right, and the triplet states are called orthohelium. All right, so let's see if these names we can give it orthohelium. Okay, so para means, well, I was gonna try to make this connection somehow. That parallel would have to do with the spins, but then it would be the opposite,
Yeah.
right? So, and I would have thought ortho meant up and
Well,
down, but
ortho-
it's just the opposite.
That's the orthogonal. They're all different spins.
Well, it could have to do, instead of having to do with the spin, it has to do with the spatial
Yeah,
posture.
it has to be the space.
Okay, so,
Otherwise, ortho and para don't make any sense.
right, so this para must apply to the symmetric space, and the ortho to the antisymmetric space.
Because asymmetric spaces, well, probably the.
Right, because if you
probably
represent
the
0, 1,
Yeah,
it's a space in a matrix, they're orthogonal.
there you go. Okay? All right, so that's a lot of detail, guys, and you know, I'm glad I had to get to it. All right, but on the next table, and so this should help you with some of those homework problems that I handed out. There's a whole bunch there, and believe me, you're going to have to work through the solutions at the same time. All right, but try to work through them. The only Hund's rule that I'm gonna hold you to is this one. All right, and that's Hund's rule number 1, and it's said explicitly in homework problem number 513, and it's called Hund's first rule. It says that all other things being equal, the state with the highest total spin will have the lowest energy. Which you think is whacked up, because you think that the lowest energy, everything would be, you know, paired up, all right?
Right, but it means that the space has more impact on the energy than the angular components.
Okay, at this level here, yeah.
So do you want us to tell you homework 13?
Yeah, I want you to try doing all those homeworks and hand in something. All right, and the reason why I want you to hand in something even though you've got the solutions is, it's got to go through your brains onto the paper. So I want you to hand in all of these homeworks. All right?
What homework was it?
I sent it in a PDF. Yeah. Okay? So I think this is great. If you look at, for example, the ground state electron configurations for the periodic table, you can start to figure out these things. Hydrogen, so hydrogen just has 1 electron. So the ground state is going to be an n equals 1 and L equals 0. So it's going to have a total angular momentum of 0. So it's going to be an S state. And what is the spin for hydrogen with 1 electron? What is the total spin? A half. And so is it a singlet or a triplet or something else?
Let's say we do something else.
So remember, it's 2.
It's a doublet, right?
It's a doublet, doublet S. So the ground state, if you look at table 5.1, the hydrogen is a doublet S.
Yeah, but it makes sense if you think
This,
plus 1/2 plus 1.
that
So
is,
it
this
should-
is the formula, L total and S total plus 1. And that's called LS
So
coupling.
that should be substitute.
And this scheme of labeling things is good for low Z atoms. All right, so once you get above a certain level, and I think it's somewhere around the middle of the periodic table, that instead of coupling the S's together and individually, then the L's together individually, and then couple the S to the L's, once you get a big, huge nucleus and relativistic effects come into play, then it makes more sense to couple the spin of an orbit with its orbit first, and then couple all of those together. So you're coupling like S1 with L1 to form J1,
Right.
and then S2 with L2 to form J2,
And then a couple of J's.
and then couple the J's, and that's called JJ coupling. All right, but that's in a different course on atomic physics. That's not what we're going to do here. Okay, low Z, this LS coupling scheme, S1 to S2 and L1 to L2 works. But if you work your way down in the periodic table, the helium ground state is going to be a singlet because it's a 1s squared, so it's going to be a singlet S. And then they put in J's in here, okay? And then the next one is going to be lithium, so that's a closed n equals 1 shell where the spins are paired, and then it's again 1 electron outside of that. So the total S is going to be a half, right? So it's going to be a doublet. So it's going to be a doublet S, all right? And then your beryllium, that forms, it's a 1s squared, 2s squared, right? And so, and then the next one is going to be beryllium, which is a 1s squared, 2s squared, then there's 1 electron in the 2p, all right? So everything's paired up except for that 1 2p electron. So the total spin is just going to be a half for that 1 2p electron. Total spin, total angular momentum is going to be 1 for the p orbital. So this is going to be doublet p. All right? But then the next state right there, carbon, is a helium, so it's got 6 electrons, right? So for carbon, you would be tempted to do this. For carbon, you'd be tempted to go 1s squared, 2s squared, 2p squared, right? And what you'd be tempted to do is say, this is an up and down, this is an up and down, and this is an up and down.
that because it's in the P, it could be a triplet.
That's right. But remember, P, all right, has, the P is, if you want, you could write it as 2px, py, pz. And what you're saying, if you want to do this, is that you'd have an up and a down in px. Well, that's possible, right? But most likely what's going to happen is this. You're going to fill up the electrons this way first. So
You're
that
gonna get
next,
up- You're gonna get ups in the three.
you're going to get ups first.
And then the downs will.
Then they'll fill in after you fill up the ups. And that's due to Hund's rule.
Yeah.
And lo and behold, you see for carbon that the ground state is a triplet P and not a singlet P. All right,
Well, that makes sense because the triplet P is lower energy.
that's the whole thing. Okay, so that's deep stuff. That is not trivial and makes your head hurt. Okay? All right, so let's get to the next section, which is the free electron gas. Is everybody kind of clear on this? Because it is not straightforward. How do you counter this in chemistry? Okay, you did get it?
Not in details like this.
But there was something about the triplet was the lower energy and everything?
I can do that.
Okay. Yeah, the good thing, Eric, is once you know physics, when you take chemistry, you enjoy it.
Yeah. Well, I've been tutoring people in chemistry without having taken it yet.
Yeah, and it was
If I just
a
take that book
class.
and I'm like, this stuff makes a lot of sense.
There you go. The class will be trivial. Okay. All right, so
Just the
now.
lab will be interesting.
Yeah. All right, the next thing we want to do is we want to look at a bigger example of now, not just 2 electrons, we want to look at a free electron gas, which is a whole bunch. All right, so let's look at a free electron gas. All right, and so this is the free electron gas. And the idea here is we started off with atoms, and we've got an idea with atoms about what's going on. And now we want to start, we eventually want to get to solids. And so to get to solids, what we're going to do is we're going to jump in and we'll go atoms to a gas. So individual atoms, and then we're going to go to gas, and then we're going to go to solids. All right, so here we go. Now, when we do the free electron gas, all right, what we're essentially going to get is essentially like a neutron star. We can start solving for a neutron star because a neutron star, instead of it being an electron gas, a neutron star you could consider a neutron gas. All right, the electrons are fermions, spin a half, neutrons are fermions, spin a half. All right, the only thing is that you don't have the repulsion, you don't have the electrostatic repulsive term, all right? So, it's really important to see. So we're going to make the very simplest approximation of a gas of fermions. So let's make this a free fermion gas. All right, and if you're thinking neutrons, there's no repulsion anyway, no repulsive force. Anyway, right? And if you're thinking electrons and protons, what we're going to do is let's ignore the electron-electron or proton-proton interaction. So that seems like a huge thing to ignore, right? For these things? We're just going to ignore those completely.
Gas.
They had to be really far apart.
All right, so we're going to ignore it. And so essentially what we're going to do is we're just going to build, here's our model. It's just a big volume with walls. This will be Lx, so this will be Ly, and then this will be Lz. All right, and we've already done this problem, by the way, right? This is the three-dimensional Cartesian coordinate
Right.
gas, no big deal. Okay, so let's write the Hamiltonian. So H times psi equals En psi n, we'll anticipate psi n's.
It's an infinite square.
All right, and what's the Hamiltonian going to be?
Negative h bar squared over 2m.
So it's going to be minus h bar squared over 2m del squared. So let's go x, y, z for Cartesian coordinates times psi plus 0 equals En psi n. Why did I write 0?
That's the potential.
Yeah, I'm going to ignore it.
You know that.
I'm going to ignore that whole thing. Okay? Now, I'm not going to go through all the solutions. You guys know how to do this. What's your general technique for this?
Separation of variables.
You have three variables, x, y, and z. So you're going to assume that psi equals x of x, y of y, and then z of z. You're going to do separation of variables. And what is each separable solution going to look like?
A sine whatever plus b sine.
It's going to look like our one-dimensional problem, right?
A sine plus b cosine.
Combination of.
That's right.
It's the infinite square. I don't break it.
It's the 1D well, it's the electron in an infinite well all over again. All right, and so the solution, I mean, is I won't go over it, but you guys should do it, is 5.38, that psi of nx, ny, nz is going to equal a radical 8 over lx, ly, lz, no surprise there, right? Because the one-dimensional, it's radical 2 over a.
Yeah, so it should be.
Yeah, so no big deal. And then it's going to be sine nx pi over lx x, sine ny pi y over ly, and then sine nz pi z over lz. Any surprises there?
No.
No. All right?
That's exactly what we got for the 3D infinite.
That's right. Exactly what we got. And the other thing that we got was this condition. What did we have? We had something like kx lx equals nx times pi, right? So that kx equals nx pi over lx.
Right.
So we can call all these k's.
Kx times
Yeah,
x.
KX,
y,
Yeah.
z.
All right, and the other thing that we got, I can't remember it, so I'll actually derive it over here. Everybody ready for one-dimensional case? It's going to be d squared psi x with respect to x squared, and then bring that over, it's going to be plus en times 2m over h bar squared times psi n equals 0. And I call this k squared. So k squared equals En 2m over h bar squared. So En equals k squared h bar squared over 2m. Everybody remember that?
Yep.
Yeah, that's right.
Okay. So what we've got over here then is, look, the energy, we have kx, ky, and kz, all right? And each one of those is going to contribute an energy when it's squared. So we have the total energy of this thing, so E total, and it's going to be, let's say kx, ky, kz is going to equal h bar squared over 2m. All right, and then we'll write it as, let's write it like this. nx pi over lx squared plus ny pi over ly squared plus nz pi over lz quantity squared. That's the total energy.
Then you can put out the pie.
Oh yeah, you can pull out the pi. So let's pull out the pi squared. And that's what it's done in the book. And that is equation 539 in the book. All right? Okay. So, let's do this. let's kind of think of this in terms of wave vectors. I like to think of it this way. E total equals h bar squared over 2m kx squared plus ky squared plus kz squared. That's the way I like to look at it. All right?
Yep.
And k's are wave numbers, right? Their units are, it's per unit length. It's numbers per unit length. Okay. So, what are the possible things that I can have? Well, I could have, this is related, so this, for example, is nx pi over lx. This is ny pi over ly. And this is nz pi over lz. All right, so what I'm going to start thinking about is this. I'm going to start thinking about these units. All right, and so maybe I'll write it like this. This is maybe the best way to write it is nx kx plus ny ky plus nz kz, where kx is pi over lx, ky is pi over ly, and kz is pi over lz. All right? Because those don't change. Pi over lx, pi over ly, those are just the wave numbers. And so the possible values of nx and y and z, what I know from the 1D well, are 1, 2, 3, 4, and so on. Okay? So what I'm going to do is I'm going to look at this whole problem in kind of a k-space. So this is a k-space, or a wave number space. All right? And this is kind of like, these are all nx equals ny equals nz equals 0. That's that first one. But look, the first total energy I could have, let's have nx. No, let's do this. This is x, this is y, and this is z. So if I have a point right here, all right, this is nx equals 0, ny equals 1, and then nz equals 0. That's a point right there. Now, is that a possible energy that I can have?
Yes.
Of course it's a possible energy, because the solution to my wave function can have nx equals 0 and nz equals 0, and have ny equals 1. It gives me a legitimate wave function.
That gives you the energy.
And that gives me the energy. All right? So then look, I can have but how about this? This would be like nx equals 1,
Everything else is 0.
and everything else is 0. Then I can have this over here, and I can have this over here, and I can keep going like this. Now notice after a while, what I'm making is kind of a grid, right?
Yep.
So I guess how would I draw that? Oh boy, my drawing's not going to work very well here. How come? There you go. All right, kind of works like that, my grid. All right, and for each one of those points, what does each one of these points represent? It's an nx, ny, and nz. In other words, it's a particular state of a particular energy. Okay? Now, can I have, let's see, a minus 1 equals nx?
No, and goes from 0, and starts at 0 and goes.
That's right. So we're only talking about positive values, because the one-dimensional case, we're only for positive n. So if this whole three-dimensional space, we're talking about one, what, octant?
One, whatever.
One octant. Yeah. So the only thing we're talking about is this one octant, where, you know,
Nx,
this
ny, and z are all greater than or
Yep.
0.
nx, ny, and z all greater than or equal to 0. Okay? Okay, so that's the first step. Now, the second step is, if I want to enclose like one of these states, So I want to say, how much volume does one state take up? So how much K-space volume does one energy state take up? Okay? And that comes back to over here. You can imagine that if each one of these represents a node, then you could encompass each one of these nodes and build a grid where the volume is essentially pi over Lx, pi over Ly, and pi over Lz. So you can show that this equals, or you can argue this equals pi over Lx times pi over Ly times pi over Lz, which equals pi cubed over, we'll just call this the volume right there, where the volume is defined as Lx, Ly, and Lz. Now remember, Lx, Ly, and Z come all the way back to our original problem. Okay? So this equals the volume so it's the
Volume of the object itself.
volume of one energy state. Okay? All right. What we're now going to do is we're going to go to, instead of Cartesian coordinates, we're going to go to spherical coordinates. All right? Why not? All right, so instead of making this a sphere, instead of making this, instead of Cartesian coordinates, let's go to spherical coordinates. Okay, so I'm still going to have this is kx, this is ky, and this is kz. All right, and so my sphere is going to look like this a little bit. All right, but real careful. Does it count for the whole sphere, or are we only talking about a part of the sphere?
Part of the sphere.
Yeah, so let's go from Cartesian coordinates, Cartesian K-space, to spherical K-space. And what we've got to do is we've got to keep the volume equal. So the only thing that matters is let's keep the volume equal. Keep the volume equal. So, in other words, in K-space, if I had a spherical volume, which would be 4/3 pi K cubed, this is my spherical volume. Spherical volume for one energy state. That has to equal, it has to equal pi cubed over the total original volume. Everybody agree?
Yes.
Okay, but, very important thing, 4/3 pi r cubed is the sphere all the way around, but we're only covering k's that are in the positive quadrant.
So it's 1/8 of that.
It's 1/8.
It's
It's 1/8. So we have to have 1/8 of this volume equal to pi cubed over the volume. Okay, so this is all for one energy state, all for one energy state. Okay? But typically what we do is we have typically, instead of having one atom, we have n atoms, and then each atom has q free electrons. So how many